Okay, good. Well, welcome all. Thanks for joining us. My name's Tim Stallard. I'm a professor here at the University of Manchester, specialising in offshore and renewable energy engineering. So you'll hear from me today, but also my colleague Diego Araya, who is a research associate supported on the Offshore Renewable Energy Hub. Okay, so this session is on wind farm modelling. What we've put together is a couple of overviews really of the work that we're doing in this space. So I'm going to give an intro just as to why we're looking at wind farm wakes in the first place, and some of the modelling approaches that are available in the literature and are being used by researchers and the industry at present, and some of the challenges with applying those to larger scale farms, right? Diego is then going to give a bit of an overview of work he's been focusing on engineering wake models, particularly around a study related to inter-farm spacing that was done last year by Fraser Nash for the Crown Estate, that looked at the spacing between farms at which impact on yield might be considered negligible or otherwise, looking to quantify that impact on yield of upstream farms. And then I'm going to talk again about some more detailed modelling, some large eddy simulation work that we're focusing on at Manchester to contribute in this area. And across the top here, we've got some of our other colleagues recognised who are heavily contributing in this area, Dr. Pablo Oro, Mina Gobriel, Karim Ali, who are PhD students working in this area, and Dave Schultz, who works with us on particularly mesoscale flows, numerical weather prediction type models. So what are we interested in first? Well, we're interested in the wakes of quite large scale farms, indeed the farms that are planned to be constructed rather than necessarily the farms that exist at present. This interaction between farms is of increasing interest to the sector, partly because there's quite a large amount of wind farms, as you may know, planned, or at least regions in which those wind farms may go have been identified. So this is a map you might be familiar with from 4C Offshore, indicating a number of all of the existing operating sites, but also several of the demarcated regions at various stages of development, with some of the yellow and orange and red regions having consenting at differing stages, for example, and the larger dark blue regions being areas of future lease areas, not consented or under construction just yet. And we know that some of these farms are going to be in quite close proximity either to existing farms, and we've seen in the media recently some disputes emerging in that area of the impact of a planned farm on the operation of an existing farm in terms of reduction of energy yield and hence revenue. And also there have been some issues around the scale for which sites could be leased and which areas of some of these polygons could be used, right? So there's increasing interest in quantifying the impact of upwind farms on downwind farms in terms of performance, both to inform siting decisions, project consenting decisions, and longer term to enhance operation of individual farms. There are obviously a number of farms in operation, and there's some evidence that wakes extend over quite long distances. This is a satellite image of a group of farms in the German Bight, which I've tried to overlay on the 4C offshore map, indicating the extent of the wakes here, with these darker blue streaks within the higher flow speeds shown by the green. The individual farms here are about 300 megawatts-ish of capacity, and you can see wakes extending almost to the shoreline here further to the east. However, even though some farm wakes have been measured in some areas, these turbines are of moderate scale compared to current turbines, and so there's also increasing interest in how the physics differs when turbines of much larger scale and much larger power density in much larger farms are deployed, where we may be going beyond the scale that the models that are used so far have been evaluated for offshore. There's obviously much larger farms also planned or have potential to be deployed if we're to realise the very large scales of power generation that could come from offshore wind longer term. And there have been some studies showing that the impact of farm wakes may well impact the capacity factor of planned deployments. Again, a few regions shown here from the Akhtar paper in Nature a couple of years back now, showing quite substantial capacity factor losses in farm, such as these dark blue regions, down to 20% reduction due to in-farm wakes, but also in regions such as over here, where we get an increasing loss of capacity factor as we go back through the array in the dominant wind direction, with the wakes of these polygons impacting the farms downstream here. So quantifying those effects to improve predictions such as this, improve confidence in predictions such as this, is the main focus. So just a bit about what we're doing in this space in Supergen. In the Supergen modelling package, which I'm leading on in collaboration with University of Oxford, largely on the tidal side, but with a bit of overlap on the wind, and with the University of Aberdeen on the ecological modelling side at the bottom there, we've got these three areas of work ongoing in this phase 2, the impact hub phase of the ORE Hub. Our focus for today is on this middle part, really, array energy yield predictions and array siting. What we are interested in doing is enabling array planning to improve confidence in yield prediction, to inform the scale up, the build out to much larger gigawatt scale of farms, and in particular to look at the development of wake interaction tools in spatially varying flows. Come back to that a bit later, and to look at the use of high fidelity modeling tools for particular sites to develop confidence in those tools. Part of this modelling work is to feed across, as Diego will explain, to some ecological modelling, which is being led by University of Aberdeen, looking at cumulative impacts of offshore wind farms and the wakes generated by offshore wind farms on offshore mixing, offshore temperatures in the hydrodynamics environment, and what that means for different population dynamics over the coming decades. So this middle part of modelling of representative sites also links into another part of the Supergen work plan for this phase, which is the development of several representative systems through which we aim to engage other researchers, such as yourselves or industry stakeholders, in improving the confidence in key modelling tools. In phase 1, there was quite a lot of work on a experimental turbine to improve confidence in load prediction, particularly unsteady load prediction tools. And in this phase, what we were interested in doing is taking that approach forward of engaging multiple research groups, multiple industry groups in model intercomparison to a physical data set, to other key problems, key challenges, key prediction needs in the offshore renewables sector. And array energy yield is one of those because it underpins investment decisions and it affects the revenue stream, etc. In some cases, such as that turbine I mentioned, we would be looking at a scaled physical system to represent an actual full-scale system, right? In other cases, we might be looking at full-scale field data to represent a subset of an actual full-scale system, right? But in the absence of those, for example, for much larger wind farms that may be developed longer term, or for specific operating conditions of those much larger wind farms, we may be interested in comparing to high fidelity model cases. And that's the approach that we're looking at further for offshore wind energy yield. The intent being that at the moment, there's a range of modeling tools which might have some uncertainty band, such as this, very schematic, obviously, and we'd like to narrow that uncertainty band by comparing to one exemplar or example case that captures much of the physics of the problem, and in the absence of a scaled system, a high fidelity model that captures lots of the physics may be an appropriate alternative. So we'll come back to that point at the end to explain how that links in. So to inform parts of those research activities that I've outlined that we're doing in the hub, we've been undertaking a review in the first phase since the hub started back in 23 of the different types of farm wake modelling tools that are available and the main challenges that need to be addressed for modelling large-scale farm wakes of large turbines, such as shown on this sketch top right. So with much larger scale farms and larger scale turbines, we have a number of interesting aspects of physics that don't all affect the moderate scale of wind farms that are in operation at present, and therefore we may need to go beyond some of the physical validation data sets that are available. For example, shown here on the top, we have a wind farm of moderate size in a weakly stratified flow. The wind farm height is relatively small compared to the inversion layer here. And so the flow across the wind farm isn't much affected by interaction with this low-level jet, the inversion layer above. As the turbine's size increases, obviously there's greater interaction with this, and the internal boundary layer is narrowed, and you get greater disruption of this stratified flow. That also occurs in different, in stable atmospheric conditions, stratified conditions, as shown by the bottom here, where we may have a lower inversion level, a low-level jet occurring, high flow speed just above the wind turbine. And if the wind turbines themselves are large, greater heights now, top tip heights approaching 300 meters in some cases, low-level jets of the order of 350 meters to 360 meters could be occurring in shallow atmospheric stable conditions. We have a much stronger interaction with that inversion layer, and phenomena such as gravity waves can occur, and the wake can extend for much greater distances downstream. So those cases are of particular interest to model, and they're getting some attention in the literature. In terms of how these wakes could be modelled, there are a number of types of tool currently available, various classes. We've identified 4 of the main classes here on the left: engineering wake models, which Diego will talk a bit more about evaluation of and use of; mesoscale models, which are kind of weather forecasting tools, such as weather research and forecasting. I'll talk about that in a moment; and CFD methods, which are typically isotropic in their mesh structure and have various pros and cons. So I've just got a slide on each of those, and then I'm going to pass over to Diego to talk in more detail about some of the work he's doing with engineering wake models, and we'll look at the use of LES to model some of these conditions in a bit more detail at the end. So briefly on each of those, engineering wake models have been widely used by the sector and are kind of the de facto tool to apply for evaluating wake losses in a farm, and are starting to be applied for inter-farm wakes. There's many formulations that exist, many of which are based on some form of Gaussian or radially varying structure, such as shown in this diagram top left, where the wake shape is modelled, recovers at a variable rate, or a variable rate between models, a rate that differs between models, to a downstream turbine's location, and then the velocity onto a downstream turbine can be calculated by sampling points, such as shown here, and that can be applied successively through the farm to get the performance of subsequent rows, as shown by this plot on the right for Horn's rev for one flow heading. Here's some SCADA data through the middle, and 2 different ways of combining those wakes by linear superposition, the black line, and by RMS. So one of the uncertainties associated with these approaches is how they are combined, and another is the individual wake models themselves. But there's a whole range of forms used. Many have been evaluated and developed, tuned, using SCADA data from actual offshore wind farms, albeit of the scale that's currently deployed, rather than necessarily these larger scales. A couple of examples at the bottom here of those kinds of approaches being applied to the much longer wakes downstream of one farm, so not just in a farm, but impinging on a downstream farm. And this was a comparison to SCADA data along the front row here, looking at the wind heading at which, looking at the variation of the SCADA data with wind heading for this second farm. So you can see the SCADA data drops off as the wind heading approaches an angle 150 degrees where the wake from the front farm hits the second farm. Right, and then as the wind direction moves around further north, that wake starts missing the farm, and you get acceleration of the flow occurring on the front of the second row of turbines. That's closer to over here, right? As the bypass flow from this one hits this one. And the blue line here is showing comparison to a quite well-used model by industry, Turbo Park, which Diego will talk about in a moment also. Captures a lot of that variation, not quite the magnitudes here of the lowest deficit, and not quite the increases here, and not quite the variation off to the side here, but a lot of the variation. These wakes are obviously quite straight, indicating a flow uniformly through the domain, but one of the challenges is that these wakes are just propagating in the direction of the dominant flow, so accounting for larger scale spatial variation is less straightforward. Moving up to a much larger scale, those spatial variations of flow are well captured by numerical weather prediction models, such as weather research and forecasting. And mesoscale models such as this are shown on the sketch top left, and in the middle here, typically over quite large spatial extents with coarse meshes, and have a ratio of 5:1 or 3:1 to zoom into regions of interest, such as this wind farm in the center here at a much smaller domain. But the smallest meshes are generally of the order of 1 to 1.6 kilometers on plan, and a pressure layer structure is used through the height, so that wind turbines are represented using a parameterization scheme distributed vertically, where a momentum sink and a turbulence production term is generally applied in those cells that are occupied by part of the area of the turbine. So those grey cells would have a momentum sink and turbulence production applied. So one of the key advantages of these approaches is they can account for the spatial variation of the flow quite well, and they're used for resource prediction in the absence of farms quite a lot, and increasingly used for simulation with turbines also included. Recent study showing top right here to comparing to SCADA data, again along the front row of a farm. This top farm here, due to the wake of this one down here, in this case, and again, variation with heading. So the SCADA data is red, slightly under-predicted by the atmospheric flow model in purple there, but reasonably good variation over the range, but in unstable conditions here, much greater variation, partly due to a larger number of samples. So quite good predictions across the front row, but the resolution means that multiple turbines can be in the same cell on plan, and there's generally less good prediction of internal farm wakes, even though the farm-to-farm wakes have been shown, such as this case, to be moderately well predicted. Okay, so those approaches have advantages in terms of spatial variation, which are lacking in engineering wake models. A finer scale version of those is increasingly used, mesoscale codes with large eddy simulation as closure in the vertical, which allow for a finer horizontal mesh to be used and similar vertical meshes. And turbines are represented using a generalized actuated disk approach, again, where momentum sinks and possibly turbulence production, but it's not always clear, are applied in the parts of cells occupied by turbines, right? What prominent example of this at present is the code WIFL, or the code GRASP, developed by WIFL, which is GPU accelerated, and enables simulation of very large spatial domains at approximately 120-meter horizontal resolution with pressure layers vertically. So these approaches have analogues with the mesoscale from before, in that turbines are parameterized, but turbines are still only coarsely approximated in the horizontal direction, with a couple of cells across the turbine width. Much finer scale models in horizontal as well as vertical comprise RANS and LES simulations. So RANS has been quite widely used with a number of different implementations, typically farms of turbines represented using actuator methods, either actuator disks or actuator farms, actuator canopy models, now used in some groups, as shown in this sketch top left, or this schematic top left from van der Laan, where here on this second frame, individual turbines are identified by their actuator disk model top farm here, generating a wake impinging on a second farm. And they showed that by just having a vertical profile of momentum extraction from the turbines in the first farm, rather than individual actuator disks, a similar wake was generated, and the actuator disk model of the second farm reports similar performance to modeling the front farm with an actuator disk. So that's potentially quite a powerful tool for making things faster. However, there are sensitivities to the turbulence model employed, as there are with other uses of RANS. And this plot in the middle here is showing quite a lot of sensitivity to the choice of turbulence closure scheme used. There are also some challenges with taking these approaches to very large spatial domains as required for wind farm wake simulation. And most studies with RANS to date have focused on quite idealized atmospheric boundary layer conditions. At a similar spatial scale, so of the order of 12 to 20 elements across a rotor disc, and with turbines operated or represented using actuated disc methods. Large eddy simulations, we're referring to as microscale because they're isotropic, are used increasingly to analyze either particular farm configurations, as shown in these plots from Mars, with a very large scale simulation in 2 different stability conditions, or particular farm layouts, such as this Horns Rev simulation, for particular atmospheric conditions, or to investigate particular aspects of flow physics, such as the formation of gravity waves, as per this figure in the bottom. So one of the main advantages over RANs is they're less dependent on the turbulence closure scheme, but we'll come back to some other aspects, such as the subgrid scale model in a moment. And they capture more of the physics than RANs, so can, in principle, provide insight to the behavior of farms in complex atmospheric boundary layer flow conditions, such as differing stability. Frame bottom left is a stable flow, and you see much longer wake extent than in these neutral conditions on the top left frame. And phenomena such as Coriolis forcing and gravity waves. However, they have to date been relatively computationally expensive, so can't be applied to the wide range of conditions that mesoscale models can. So what we're interested in the hub is looking at intercomparison of several of these model types. Here's just a sort of overall summary of those types, and facilitating that intercomparison of model types. There are a couple of ways by which that could be done. Obviously, the ideal is to compare models to real physical data. And there are some such data sets that exist. I don't expect you to read all of this. Have a look at the recorded version in due course, if you would like. There are some data sets that exist, such as these transects obtained as part of the X-Wakes project in proximity to farms in the German Bight. However, there are challenges with assessing models such as MLES, and all the different types of model for these particular conditions, not least the time taken for the flow to propagate over the extent of the domain, whether the flow is steady over those intervals, and knowing what the turbines are actually doing, since some of the data is commercial. So there is value in evaluating models relative to each other, particularly where some of the models represent certain conditions. So what we're looking into further is looking at undertaking a number of idealized configuration studies, such as just a couple of square layouts, as we'll see later, for particular atmospheric conditions to better understand the details of the flow and to facilitate a intercomparison of models, perhaps involving others, such as yourselves or others, in that intercomparison in due course, for selected cases that represent atmospheric conditions and farm spacings of interest. So that was a fly through. I've used a bit of our time. Apologies, possibly slightly more than I should have done. But I'll pass over to Diego now to talk through what he's been doing and is doing with engineering weight models for assessment of buffer zones, informing ecological models, and evaluating capabilities relative to high fidelity codes. Please bear with us while we swap slides. Thanks.
Thanks, Professor Stallard.
So just while Diego's getting his slides up, I'll just remind everybody, as per Lee and Rosie's comments in the chat, this is being recorded, but you're not, it just us. So you can look at the recording later. And if you've got any questions, please just post them in the chat so everyone can see them. Thanks.
Okay, I hope you can see my screen now. Correct? Okay.
That's great. Thanks, Diego.
Okay, so thank you for joining us today. And my name is Diego Araya. I am a research associate working here at University of Manchester. And I will be presenting today some of the applications of engineering with models, as mentioned by Professor Stallard. There are 3 main aspects or topics I will cover. The first one is about farm-to-farm interactions. This is an analysis of the buffer zones between farms and how do they impact the yield, which is quite relevant to get deployment of the larger scale wind farms we need to get to achieve net zero targets. The second point is about surface wind speed, wind deficits. So here we have a collaboration with the University of Aberdeen, with Professor Beth Scott and Dr. Ariana Sampolo. This work is mostly focused on the impacts of offshore wind on ecological indicators, how do they affect the marine life, the ecosystem. So we're trying to work on how we can use engineering wave models to support the development of that work. And the last part is assessing engineering wave models with higher fidelity models, how we can understand better the advantages and limitations of these models, particularly for large arrays. And so we can then work out under what circumstances we can apply them with some confidence, and when we need to take care of some other details. So the first part here is the farm-to-farm interactions. We start with this Fraser-Nash report that was released for the Crown Estate last year. This report is analyzing the buffer zones, considering two idealized 1 gigawatt farms. And these are the three main conclusions I took from the report. First one is the farm-to-farm wake losses are small compared to internal wakes. Second one is that farm interactions wake losses become vanishingly small beyond 20 kilometers, and that for achieving the highest yield, if you have a limited area, no buffer zones need to be introduced to achieve that. So looking at the report, in the right-hand side, you see some pictures I extracted from there. You have, in the right-hand side, the layout. You have two 1 gigawatt farms. Basically, those are square arrays. And in the middle, you have the wind data. Well, the top is the wave distribution curves for all the wind directions. The bottom, the wind rows. And the first key observations are that if you look at the wind rows, the main heading is not really aligned with the direction of interaction between the two farms. So we have wind coming from the west, and the farms are aligned north to south. The second observation is all the report is done using the Turbo Gauss model or Turbo Park. And so those observations prompt some questions that we wanted to analyze. First one was, what if the main heading is fully aligned? So what if the main wind heading is aligned with the farm interactions? The second is, what happened with other modeling choices? If we choose to use different engineering wave models, how does that change the conclusions? And finally, how does the size of these farms affects the conclusions as well? First step was to reproduce Fraser-Nash results. In the right-hand side, you have two plots again. The top plot shows the variations of the net annual energy production as a function of the power density that is varied for a single farm, and changing the spacing between the turbines. So the dots shows the results from Fraser-Nash. The solid line shows this work. At the bottom plot, you can see a similar analysis, but now we have two farms interacting to each other. The blue line shows the net annual production, and the green line shows the losses. So from these plots, you can see that I managed to reproduce the Fraser-Nash results and basically set the methodology for the next of the analysis. You see some variability between the two cases, and that's mainly due to the fact that I had to digitize some of the data from the report. So it's not usually exactly the same data, so it is expected to have some variations, small variations. Okay, so one of the things we try to do is what happens if we use different models. There are a range of different modeling options. They differ in the way they assume the shape of the wake behind the turbines. So we have from the Jensen model, that is a top hat distribution showing red in the middle plot, but also two more developed Gaussian shapes as the super Gaussian model showing blue. And of course, there are many things happening in these models. All of them are trying to capture more physics as they are more developed. Things like what is the local turbulence intensity, what are the type of superposition models they used, or the different model coefficients you need to tune from SCADA datasets. So we decided to try a range of models using PyWake. PyWake is the library developed by Technical University of Denmark to run these engineering models. And then we also have the question of what happened if we aligned the windrows to the farms. So we rotated the windrows 5 times, so 30 degrees, 60 degrees, 90, and 120, and explore what changes in the outputs occur. So the first thing here is looking at just changing the model. Here you see the bottom axis, the distance between the two farms. In the left axis, sorry, in the vertical axis, you see the total losses. And the first thing you see is the Fresnel report seems to have chosen the most conservative model consistently, predicting the higher losses. We see a lot of disparity between the models. Gaussian models seem to be located between 4 and 6% losses for this particular layout or array. And the losses plateau beyond 5 to 40 kilometers, depending on the model. So the Jensen model goes plateau about 5 kilometers downstream, whereas the Turbo Park model goes beyond 20 kilometers. You can see the plateau. Another point here is when you change the rotation or the heading, we only notice a small change in the losses. It's a slight increase in the losses, but it's not significant. So we say it's little sensitivity to the main wind heading. Then if we separate from the previous plot, from the net losses, just the interaction losses separated from the internal wake losses, we have this picture on the right. Again, the Turbo Park model is the one that is showing the most conservative approach. And at 20 kilometers, you see losses are about 0.5%, so above 0.5%. And at 10 kilometers distance between the two farms, you see losses over 1%. I will come back to this black line in the coming few slides. So I want you to remember that a bit for a bit. Before going into that analysis, I just want to highlight also the variation in the power density changes also the net losses. So when you have higher power density, you can have higher farm losses as well. And a key finding here is also that 1.2% loss at 10 kilometers for a 1 gigawatt farms is still considerably a large amount of energy. Okay, so next question is, what happens if we have existing farms that are smaller in size? So we decided to extend the analysis and say, let's keep farm A the same, but farm B try different arrangements. So I tried 3 different farms, 250 megawatts, 490 megawatts, and 240 megawatts. And they all have different shapes. So the two farm B, S1 and S2 are square arrays, whereas the last one I decided to use a rectangle. So we have different aspect ratio and see also how that affects the performance of the farms. In the bottom plot, you see what is the net annual energy production captured by Jensen model and Turbo-Gauss models. These two models represent the two extreme cases in the previous slides. And you see that the losses for the Jensen model is between 2 to 3% for all these farms operating in isolation, whereas for Turbo-Gauss predicts internal wake losses between 5 and 8%. So the question next is how do they interact with each other? So here we analyze the case for 10 kilometers only, using the windrows pointing in the northern heading. And at the bottom, you see a table. The most important column is at the right-hand side in red. You see three different colors in the table. Gray is showing the internal losses, the interaction losses. When you look at the total energy yield as a global, the blue one is showing the results when you look at it from the farm A perspective, and the green one is showing the results from farm B perspective. So from the previous slide, we saw that internal wake losses at 10 kilometers, interaction losses at 10 kilometers were in the order of 1%. But if you look at from the farm B perspective, now these losses can be in the range of 2 to 3%, depending on the farm size and the farm shape. So we can extend that analysis from the previous slide at 10 kilometers and going to the whole range from 2 to 80 kilometers spacing. And here is again the black line I mentioned before. For these smaller farm cases, you can see that the total interaction losses, seems to be lower than the Fraser-Nash report reference black line there. In red, you see the previous case, the previous slide, 10 kilometer. But if you then try to look at from farm A perspective, this could be a different developer, a different company. The case is much better because you have a smaller farm next to you, so you don't see much interaction losses from a smaller farm. But then if you go to the farm B, which could represent an existing farm, then the losses could be significantly more. Here you see at 20 kilometers, we have a interaction losses of greater than 1%, and at 10 kilometers, the losses could be in the range of 2 to 3%. Then, if you look at specifically farm B, S3, the one that has a rectangular shape, you can see also the effect of the aspect ratio. This farm, because it's facing 1/3 of the turbines directly to farm A, is mostly affected by the interaction losses from farm A to farm B. And then the second farm B, S2, is the one that has a higher capacity. So internal wakes become more important, and then the interaction losses are not as significant as farm B S1 or farm B S3. Okay, so the next part, this is a brief description of an ongoing work in collaboration with Aberdeen. So they use an oceanic circulation model called FVCOM to analyze the effects of wind farms on marine life. There are two parts of this. One is what happens with the tower under the sea. And then there is the other part, what happened with the wake effects on the surface of the sea and how that changes the driving forces, circulations, local circulations, and how that then will affect the turbidity levels, temperature gradients, and therefore the marine life. So the project here is trying to improve upon previous work where they try to map a Gaussian weight deficit for the whole farm into this FECOM model. So the FECOM model needs a top boundary condition for the wind at 10 meters height. And this coarse approximation was used before to try to understand what are the potential effects of these into marine life. So the idea now is try to improve on that and say, what happens if we use engineering wake models to map wake deficit, not at a farm scale, but at turbine scale, and see how that affects marine life. So in collaboration with Ariana, we are developing a Python library to map these turbine scale wakes deficits onto the top boundary conditions of the FECOM oceanic circulation model. We have to use SCADA data and also area data sets to set up the model. We run the model for every time step in a time series, and then we pack that into an etcdf file that FECOM uses as an input file. So in the coming months, we are going to be hopefully delivering some work on this, on how the comparison between the previous approach of a large farm scale Gaussian deficit compares to turbine scale deficits. And so more on that coming later in the coming webinars. And the last part here is how we can use engineering web models to compare, how we can assess them, comparing them with LES simulations that we do in-house from other colleagues. So here you see small, well, this is a large array. So these are idealized arrays of about 4 gigawatt each, 16 by 16 turbines with 50 megawatt capacity. And for this specific case, I'm showing how you can address or use a PyWake to calculate power output for these wind farms. I chose specifically one thing that is important, which is how to consider the wind direction variability around the mean. Typically, you have a heading in a CFD model. It's not representative of what happens in nature and reality. So you always have some variability in the wind directions. And here I show you just briefly how these can change the total output of power from farm 1 and 2. The LES case is a pressure-driven boundary layer. Professor Tim Stallard will show you after this what are the limitations of this, or what happens when you need to run stable conditions. Then we try to compare for this pressure-driven boundary layer LES case. We extracted some transects of wind speed deficit at half height. Here in the plots on the right, you see quite a lot of noise. Pretty much is because the farm is very big, so all these spikes represent proximity to turbines in the array. The blue line represents the LES reference case, and then you have two separated, well, the green line and the orange line. The orange line is using no wind direction uncertainty, and the green line is considering a 7.5 degrees standard deviation for the wind direction. Some of the observations here is that within farm, so in-farm wakes, are relatively well captured by Turbo-Gauss model. If you see in this region here, all these dashed lines represent the average over the distance between the maximum turbine and minimum Y coordinates. So those three lines are quite close together, and if you use a uncertainty in the wind direction, then the averages come closer together with the LES. As you move downstream to the transect number 6, you see that differences start to emerge. Part of this is because the engineering wave model is unable to capture the slowing down of the flow around the edges of the wind farm. So the onset flow you see at the beginning of farm 2 wouldn't be the same in both cases. Also, in the top of this plot, you see that in the far wake of farm 1, the engineering wave model start to overpredict the recovery of the wake. If you go farther downstream, you can still see more differences in the wake. Again, local maxima is shifted compared to LES. LES is able to capture some bypass flow, so the wake will change or will be deflected. And so that is not something the engineering wave models can do. And also you can see that because all these changes are happening as you move downstream for large scale farms, then engineering wave models have a difficult job trying to capture these changes. So some conclusions here are the main thing is that Turbo Gauss model used by Fresnel report was consistently the most conservative. Second one is the internal wakes are dominant, as stated in the Fresnel report, and the interaction losses can be small, but it's also a matter of perspective. You have smaller existing wind farms, they could see an important interaction losses of up to 2-3% at 10 kilometers. So, and even beyond, so greater than 1% beyond 20 kilometers. We also see that power density also plays an important role, as do the aspect ratio. Sorry. The other is we are doing ongoing work to further assess engineering wave models comparing to high fidelity models, and also we are working with collaboration with Aberdeen to use these models to inform other important decisions in the industry. So I think I now can come back to Professor Tim Stallard.
Thanks, Diego. Just get my screen back up. Oh, sorry, everybody. Yeah, thanks for the overview. I hope that was clear for everybody. Been a question in the chat, so hopefully my reply to that makes sense. If you'd like to pose any more, please just put them in the chat there, and we'll try and address them as we go through or at the end. So we're a little bit tight for time, partly because I ran over at the start. My apologies. So I'll just do a quickish run through of this. Mine's mostly a picture book anyway, with some examples of some work we're doing in this space. So if you want any more detail on any of this, you can pick it up with us afterwards. And with my colleagues, Pablo Oro, who is also co-supervising with me, Mina Gabriel, the PhD student who's doing a lot of work in this area. So a quick overview, building on the topics I introduced earlier about large eddy simulations and building on some of the stuff we've just seen from Diego about comparing to these types of models. So as Diego outlined at the end, we've started doing comparisons of LES predictions of wake structure in pressure-driven boundary layer flows, so a sort of classical logarithmic profile, to engineering wake models and to other codes. One of the powerful aspects of large eddy simulations is that different stability conditions can be investigated further. And as I showed on that overview slide, this is one of the main areas that it's used for in the literature. So differing stability conditions can occur as temperature changes. Here's the day to night transition. The black line or black band here is the occurrence of very stable conditions, the grey stable. So as these conditions occur, as we get a temperature transition, from day to evening. We get the stable boundary layers occurring with a lower jet height as shown by the velocity profile on the left here, and this can be up to about 30 or 40% of the time, right? In terms of wind speed, generally occurring at these speeds below rated speed, but then that's when we want to maximize power production from farms. So rated speed of various turbines is about 12 and a bit meters per second. So, increasing as our speed goes down. And that's where we're particularly interested in farm interactions because power output needs to be maximized. And because thrust coefficients are maximum, so wake's the largest extent. So the impact on the boundary layer is that you get these lower inversion layer heights, which can be of similar scale now to wind farm heights, and therefore greater disruption of the boundary layer flow due to the turbine farm itself. Okay. So modeling these flows raises a few challenges. Computational cost is one, but that can be bypassed by applying sufficient compute resources for now, and by selecting the appropriate combination of resolution and subgrid scale model, which is the key driving factor here. So one of the investigations we've been doing is what resolution is needed for different boundary layer conditions. This is a neutral boundary layer and 3 different mesh resolutions. Oh, sorry, one mesh resolution here, sorry, a central mesh resolution of 12 elements per turbine diameter. Here, the jet height is about 6 turbine diameters in height, the inversion layer here. And we've got the wind speed profiles through that boundary layer, all pretty similar with subgrid scale model at this resolution in the central plot here. Whereas on the left here, we've got a stable profile, right, where the same subgrid models on the same resolution are giving quite a range of jet heights and disparity of conditions there, right? So for a conventionally neutral boundary layer, the mesh could be coarser, and we still would get similar predictions, or the outcome on this mesh resolution is similar irrespective of the subgrid model used. So much more sensitive to stable boundary layer conditions. So we've looked at different resolutions with the stable boundary layer conditions to establish what combination of conditions the model needs to be set up with, and also to establish which subgrid scale model is most appropriate for wind farm modeling, i.e. the one that's most robust and most insensitive to mesh resolution. So here's a very coarse mesh, and you can see there's lots of variation with subgrid model. Here's that medium mesh, and here's a mesh with 45 elements across the rotor diameter. We've got quite good convergence of the different methods and to a spectral solution by Gade et al. From a few years back now, right? But if we track across to this middle one, several of the cases, particularly the blue line and the red line and the green line through here, are very similar on this 12 resolution case. And in fact, still quite similar over here. So we found that the AMD and TKE and the SDS are quite are less mesh dependent than the others here, and more robust, therefore, for wind farm flow simulations. We've been taking that approach forward then, just the blue line on the left here, which is very similar to the D45 case on the previous slide, to analyse different farm configurations. I only have a few slides to talk you through what we're doing, so I will close quite soon. One of the challenges with wind farms is obviously the domain needs to be much bigger than for the precursor flows, as shown on the left there. And we're looking at domains of tens, now hundreds of kilometers in extent, with mesh resolutions of 24 meters as the finest, right? Turbines are represented using actuated discs generally. We've done single turbine simulations with actuated lines, as have others, but they tend to be too fine for all farms. So here's a farm in a stable boundary layer flow. We can see the flow is nearly uniform onto the front row, but you see this flow curvature occurring due to the inversion layer heading being slightly different and shifting the wake off to the side further downstream. The average wake structure, then, we can output for comparison to the kind of things that Diego was showing before. And we see, again, dependency on subgrid scale model, not so much on the front row here at this profile, but starting to be disparities by a few diameters downstream of the farm, with 4 of the methods agreeing quite well through here, including the AMD method, which is quite independent of mesh structure for these resolutions, but quite different for some of the turbulence closures models, some of the SGS models. The LAS DDD here at the back is showing more rapid recovery than the others. And we see as a consequence of this different recovery, different per row performance recovery, different per row performance through the farm. So whilst Diego hasn't shown this yet, we're comparing the in-farm performance also between the methods. Just a direct comparison to a conventionally neutral boundary layer flow, just to show you the difference. So this flow doesn't have that low-level jet. The inversion layer is 6 diameters above the wind farm rather than just about 2. So much less constrained. Wake is lower deficit and extends less distance downstream. And there is a greater drop-off from the front row to the next row because the turbine lines are aligned. And the overall power is slightly higher, as shown from this table top right, but less sensitive to subgrid scale model. We've been taking those methodologies and applying them to much larger farms now to investigate the interaction of the stable boundary layer flows with farms of the scale that Diego was explaining. Here's a screenshot or an output of the flow field around a 4 gigawatt wind farm in a domain of 240 kilometers in length with 256 turbines, just to give you a sense of the scale. And you can see these diagonal bands occurring here where we've got pressure fluctuation induced by the gravity wave that's forming over the farm and causing a small velocity fluctuation outside the width of the farm. But the main interest is the wake extent here and the impact of that on downstream farms. So to wrap up, what we're using LES for, and indeed some others are, is analysis of atmospheric boundary layer flows and their interaction with wind farms at large scale. LES allows captures the physics of Coriolis forcing, atmospheric stability, and in principle gravity wave formation. However, large computational domains are needed, potentially with high computational cost, but appropriate selection of the combination of subgrid scale model and of resolution can bring that down somewhat compared to a full spectral solution with certain other subgrid scale models. We're using this approach at the moment, anisotropic minimum dissipation subgrid scale model, to apply to very large farms such as those that Diego was analysing. 2 4 gigawatt farms here interacting at 20 kilometer spacing, and you see contours of the velocity deficit downstream, which we're comparing to the engineering weight model and others. So the intent here, as per the end of my first intro slides, is to develop some high fidelity cases that we can use for model intercomparison to these engineering weight models, but also other codes, as per the diagram bottom right, to better understand what the variability is between those models and what the variation is in wind farm yield. Thanks very much. Sorry, just 1 minute. Thanks. Thank you. Okay, so I'll just drop my slides, and apologies for someone turning up at the door. So thank you all for your time. We have drawn to a close because I was a little bit slow in the first bit. I do apologize. But thank you for taking the time to listen. Thank you for the comments that you have sent in the chat. We'll try and respond to those straight afterwards. If you'd like to discuss anything further, please let us know. Lee and Rosie have recorded, and we'll put the version online, and we'll share the slides also. So thanks very much. I think we'll close there.